Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we are continuing with integration, looking at the last of 3 videos where we will discover how integration might be applied. This video's applications relate to volume and surface area of revolution, so if you're ready to learn, then let's get into it. So as the name of this video suggests, we'll be looking at the volume and surface area that you can get from revolving a function around the x-axis. So we take our function f of x in the 2D plane, xy, rotate it around the x-axis by 2 pi, and it will carve out this whole 3D shape. So if we look for, firstly, the volume of revolution from this, and we consider our small disk here, the volume of this disk will be delta V approximately equal to pi times the radius of this disk, which is just going to be y at that point, so pi y squared, times the width of the disk, delta x. You can imagine sort of a cylinder here, and therefore, when we sum up all these small disks, we would get our total volume is equal to pi, we'll take the pi out as it's a constant, times pi, well the limits are from a to b of our function f of x, times y squared dx. It's quite a simple formula for the volume of revolution. For the surface area of our small disk, which I'll denote as delta big S A, we'll need to consider what is the path length of our function along our disk, and we'll have to multiply that by the circumference of the disk, which will be 2 pi times the radius y. So therefore, delta SA equals 2 pi times y times by our path length, delta S, and this is the same delta S that we've been using in previous videos for the path length. We also know that delta S is equal to the square root of 1 plus delta y by delta x squared, all square rooted, times by delta x. And so when we go to integrate, we'll have our total surface area, SA, equal to 2 pi times the integral between a and b of y times by 1 plus dy by dx squared, square rooted, dx. And that's our integral for working out the surface area from revolution. For our first example, let's consider a paraboloid, which will be defined by our function y equals square root of x. So this line here represents y equals square root of x, and we'll be considering the range of x between 0 and 1. And therefore, to work out the volume, we'll be using v equals pi times the integral from 0 to 1 of y squared dx, which equals pi times 0 to 1 of x dx, which is just pi times half x squared on the range of 0 to 1, which is just pi over 2. And that's the exact volume of our paraboloid between 0 and 1. If we wanted to know the surface area, we'd use the equation for that, so 2 pi times the integral from 0 to 1 of y times 1 plus dy by dx squared, all square rooted, dx, and that's equal to 2 pi times the integral of 0 to 1 of root x times by the square root of 1 plus 1 over 4x dx. So if we combine all that, we'll have 2 pi times 0 to 1 of the square root of x plus a quarter square rooted dx. Now when we perform that integral, we'll have a factor of 2/3 come out, so we'll have 4 pi over 3 times by x plus a quarter to the power of 3 over 2 on the range from 0 to 1, and that's just equal to pi over 6 times 5 to the power of 3 over 2 minus 1. And so that's the exact surface area of this paraboloid between 0 and 1. Next, let's consider a sphere. So all we're doing here is rotating this hemisphere around the x-axis by 2 pi. And so we'll describe this by x squared plus y squared equals a squared, as we're going from minus a to a. So the radius of our circle, and therefore of our sphere, is a. And that will mean that y equals the square root of a squared minus x squared. So to work out the volume, we just sub it in again, that volume equals pi on the range of minus a to a times a squared minus x squared times dx, because this would be a half, but we're using y squared, so it's just a squared minus x squared. And that's equal to pi times by a squared x minus a third x cubed from minus a to a, which gives us, as we should expect, 4/3 pi a cubed as the volume of a sphere. And then surface area is equal to 2 pi times integral from minus a to a of the square root of a squared minus x squared times by 1 plus x over a squared minus x squared square rooted, all squared, and then that all square rooted times by dx, and that's going to be equal to 2 pi. Now this should simplify nicely if we put this square root in here, so we'll get all of this square rooted of a squared minus x squared, so that's times by our 1, plus, and when we square this bottom of the fraction, we'll get another a squared minus x squared, and on top we'll get an x squared, but this will cancel out with our a squared minus x squared that we've put in, so we just have an x squared there, all square rooted dx, which equals 2 pi integral of minus a to a, and I forgot the limits here, of just a dx, which gives us our 4 pi times a squared, as we should expect for the surface area of a sphere. Today we have seen how integration relates to the volume and surface area of revolution. This not only draws an end to our 3 videos of applications of integration, but also to the integration section of the functions topic. In the next section, we'll be looking at partial differentiation. So if you want to learn more, I'll see you there. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.